OO Development Lifecycle and Modeling. In this video, we are going to see about OO Development Lifecycle and Modeling. Object-Oriented Development Lifecycle is also known as Classic Lifecycle Model or Linear Sequential Model or Waterfall Model. The basic software development lifecycle consists of analysis, design, implementation, testing and refinement. Its main aim is to transform users' need into a software solution. The development is a process of change, refinement, transformation, or addition to the existing product. The software development process can be viewed as a series of transformations where the output of one transformation becomes input of the subsequent transformation. The goal of object-oriented development lifecycle are given as follows. The software development process, building high-quality software, object-oriented systems development, use case-driven systems development, prototyping, rapid application development, component-based development, continuous testing and reusability. Software development process. In this video, we are going to see about software development process. Software development process is alternatively referred to as software lifecycle and software development phases. The software development process is a set of steps that a software program goes through when developed. The essence of the software process is the transformation of users' need to the application domain, a software solution, the software process, the waterfall approach to system development. Building high-quality software. In this video, we are going to see about building high-quality software. There are two basic approaches to system testing. We can test a system according to how it has been built. Alternatively, we can test the system with respect to what it should do. Quality measures are given as follows. Correspondence, correctness, verification, validation. Correspondence measures how well the delivered system corresponds to the needs of the operational environment. It cannot be determined until the system is in place. The representation of correspondence. Correctness measures the consistency of the product requirements with respect to the design specification. Illustrates the correctness. Verification is to predict the correctness. Validation is to predict the correspondence. Represents the verification and validation process. Object-oriented systems development approach. In this video, we are going to see about object-oriented systems development approach. Object-oriented systems development activities are given below. Object-oriented analysis, object-oriented design, prototyping, component-based development, incremental testing, use case-driven system development. Use case is the name for the scenario to describe the user-computer system interaction. Object-oriented analysis. Object-oriented analysis concerns with determining the system requirements and identifying classes and their relationships that makes up an application. Object-oriented design is used for the following. The goal of object-oriented design, OOD, is to design the classes identified during the analysis phase, the user interface, data access, the OO system development approach. OOD activities include design and refine classes, design and refine attributes, design and refine methods, design and refine structures, design and refine associations, design user interface or view layer classes, design data access layer classes. Prototyping. In this video, we are going to see about prototyping. Prototyping is an important part of OO analysis as well as the implementation along with the design. Prototyping can play an important role when it comes to dealing with system aspects that may not be described because of a reduction for insight. A prototype enables to fully understand how easy or difficult it will be to implement some of the features of the system. It can also give users a chance to comment on the usability and usefulness of the design. One of the best examples of prototyping is GUIs or graphical user interfaces. Types of prototypes are given as follows. A horizontal prototype is a simulation of the interface. A vertical prototype is a subset of the system features with complete functionality. An analysis prototype is an aid for exploring the problem domain. A domain prototype is an aid for the incremental development of the ultimate software solution. Component-based development (CBD). In this video, we are going to see about component-based development (CBD). CBD is an industrialized approach in the software development process. Application development moves from custom development to assembly of pre-built, pre-tested, reusable software components that operate with each other. The object-oriented paradigm emphasizes the creation of classes that encapsulate both data and the algorithm that are used to manipulate the data. If properly designed and implemented, object-oriented classes are reusable across different applications and computer-based system architectures. The integration of the already existing software components accelerates the development process. If the right components are chosen, the integration aspect is made much simpler. The component-based development. Rapid application development. In this video, we are going to see about rapid application development. Rapid application development (RAD) is a set of tools and techniques that can be used to build an application faster than typically possible with traditional methods. RAD does not replace SDLC but complements it, since it focuses more on process description and can be combined perfectly with the object-oriented approach. RAD model is a high-speed adaptation of the linear sequential model in which rapid development is achieved by using a component-based construction approach. Used primarily for information system applications, the RAD approach encompasses the following phases: business modeling, data modeling, process modeling, application generation, testing and turnover. The diagrammatic representation of RAD model. Incremental testing. In this video, we are going to see about incremental testing. Incremental testing is the process of verifying the interfaces and interaction between modules. While integrating, there are a lot of techniques used by developers, and one of them is the incremental approach. In incremental integration testing, the developers integrate the modules one by one using stubs or drivers to uncover the defects. This approach is known as incremental integration testing. Software development and all of its activities including testing are an iterative process. If we wait until after development to test an application for bugs and performance, we would be wasting thousands of dollars and hours of time. Incremental testing methodologies. Top-down integration, bottom-up integration, functional incremental, reusability. In this video, we are going to see about reusability. A major benefit of object-oriented system development is reusability, and this is the most difficult promise to deliver on. Reuse strategy are given as follows: information hiding, that is encapsulation, conformance to naming standards, creation and administration of an object repository, encouragement by strategic management of reuse as opposed to constant redevelopment, establishing targets for a percentage of the objects in the project to be reused. The essence of the software process is the transformation of users' needs into a software solution. The OO SDLC is an iterative process and is divided into analysis, design, prototyping, and implementation and testing. The reusability. Static modeling. In this video, we are going to see about static modeling. Static modeling develops the static structure of the software system in terms of objects. Static model used in object-oriented analysis and design OOAD methodology is called an object model. Static modeling identifies the objects, the classes into which the objects can be grouped into, and the relationships between the objects. Static modeling also identifies the main attributes and operations that characterize each class. Object-oriented modeling and design provides better understanding of requirements, cleaner design, and more maintainable systems. The process of object modeling can be visualized in the following steps. Identify objects and group into classes. Identify the relationships among classes. Create user-object model diagram. Define user-object attributes. Define the operations that should be performed on the classes. The characteristics of an object model are given below. In an object model, all data is stored as attributes of some object. An object model completely defines the system's functionality by specifying not only the data, but also the operations on the data. The attributes of an object are manipulated only making use of its operations. The only way of accessing the values of an object's attribute is through its operation. An object can manipulate another object only through an operation offered by that object or using objects' interfaces. The process of object-oriented analysis and design is one of elaborating an object model, increasing its detail and scope until enough information is obtained to construct a static model of the system. The object model is the principal output of an analysis and design process. Objects identified during analysis are fully decomposed and expanded in design stage. The object model is a central pillar of an analysis and design. The object model defines the computable entities in the system. The dynamic and functional models also operate on the objects, attributes, and operations being defined in the object model. An object-oriented model uses information hiding to minimize dependence on global state information. Object-oriented model uses various object-oriented abstractions like classifications, inheritance, aggregation, and polymorphism. Advantages of static modeling. Shared data areas are eliminated in an object model. Objects communicate by exchanging messages. This reduces the overall system coupling. Objects are independent entities. Changes in implementation of a class do not impact on the design of the entire system. This enhances the reuse of the system. Objects can execute either sequentially or in parallel. There is a clear mapping between real-world entities and object within the system. This improves understanding of the design. Objects formed are relatively stable over time. This in turn aids in reuse of results of analysis. Object modeling avoids shifting the underlying representation of the system as it progresses from analysis to design to implementation. Object-oriented concepts can be used to provide a smooth transition between the different stages of system development like analysis, design, and implementation stages. Object modeling creates building blocks from object and grouping of objects. Structured system analysis and design methodology uses chunks of data and functions as the building blocks, hence it provides a higher level of abstraction. Elements of static modeling. In this video, we are going to see about elements of static modeling. The object model forms a conceptual framework that brings about object orientation. Abstraction is the basic principle behind object models. The elements in the object model are categorized into two types: major elements, minor elements. The major elements are mandatory and emphasize on the necessary conditions. The minor elements emphasize on the sufficient conditions. The minor elements can be absent in an object model. Abstraction. In OOAD, abstraction provides a mechanism for managing and communicating complexity of the system. In object-oriented programming, abstraction aids in reuse and encapsulation. Abstraction denotes the essential characteristics of an object that distinguishes it from other kinds of objects. Abstraction permits us to concentrate on the similarities between objects. For a particular view, it exposes only the essential characteristics of an object while hiding its essential details. A single entity may have many abstractions. Abstraction varies according to the perspective of a particular viewer of the object. The principle of least astonishment states that an abstraction captures the entire behavior of certain objects, no more or no less. It offers no side effects that go beyond the scope of abstraction. The properties of a good abstraction are as follows. Abstraction should be well named. The meanings, intuitions, impressions, and expectations implied by a name accurately reflect the use of the abstracted entity. Abstraction should be coherent. It has a related set of attributes and behavior that makes sense from the viewpoint of the user. Abstraction should be accurate. The abstraction contains only those attributes or behavior that is part of the entity being modeled. For example, the web server should not maintain a utility to rename files. An abstraction should have only the minimal details of the entity. The abstraction should not contain unnecessary attributes or behavior. For example, a pen does not need description of its owner. An abstraction should be complete. It should encompass all the attributes and behavior necessary for the object to perform an action. Major elements of an object model. In this video, we are going to see about major elements of an object model. Major elements are necessary to establish the characteristics of the object model. Major elements are as follows: classification, encapsulation, modularity, hierarchy. Classification. Classification in which the entities that share the common characteristics are grouped into a class. Consider a person class that can have attributes such as name and address. The instances of this class, that is objects, can be Akhil, him. We can also say that the objects Akhil, Joe, and him are classified as a person class. Encapsulation. Encapsulation is the mechanism that binds together code and the data it manipulates and keeps both safe from outside interference and misuse. Encapsulation thus aids in data hiding by providing access to an object's data only through the operations it offers. This is called an interface. These external interfaces provide a set of methods that accepts and responds to a particular kind of message. Encapsulation separates interface details from the implementation details of an object. For example, a remote acts as an interface to the TV operations. To operate a washing machine, it is not necessary to study the internal working of the system. An understanding of the set of interfaces like buttons or switches provided by the washing machine is sufficient to operate the system. From the implementation point of view, encapsulation specifies the scope of the data. A private data is accessed only by its class members, while a public data can be globally accessed by any class. Protected data is accessed only by the members of the class and its child classes. Modularity. Modularity deals with partitioning a program into individual components to reduce the complexity of the system developed. Modularity is a property by which a system can be decomposed into a set of cohesive and loosely coupled modules. These modules can be implemented, compiled, and tested separately. Then they can be linked together to form a complete executable program. Encapsulation and modularity provide a bar around the abstraction. Hierarchy. Hierarchy is the ranking or ordering of abstraction. In complex systems, there are two most important hierarchies. They are the class structure and the object structure hierarchies. Class hierarchy is a mechanism that is used to express the similarity between classes. Class hierarchy portrays the generalization or specialization relationship, making common attributes and services explicit within a class hierarchy. Generalization tells us what the similarities between the classes are. Specialization tells us what the differences between the classes are. A generalized class is a superclass, while a specialized class is a subclass. For example, person is a generalized class and employee and student are specialized classes of the person. The object hierarchy is represented using aggregation. Aggregation is used to treat a collection of objects as a single object. It groups logically related structures. For example, a car consists of tires and an engine. Decomposition is the opposite of aggregation. An association can be viewed as a weak form of aggregation or as a data-oriented relationship between two entities. The minor elements of object modeling. In this video, we are going to see about the minor elements of object modeling. The various minor elements of the object model are explained as follows: persistence, typing, concurrency. Persistence. Every object in a system takes up some amount of space and exists for an amount of time. Persistence is a property by which an object transcends time or space. The object maintains its state even after its creator ceases to exist. The object's location also moves from the address space in which it was created to another address space. The different types of persistence usually offered by programming languages are: maintenance of transient results in expression evaluation, maintenance of local variables in procedure activations, maintenance of global variables and heap items, In the domain of database technology, persistence is offered by the data that exists between executions of a program, exists between different versions of the program, outlives the life of a program. Typing. Typing of a class prevents objects of different types from being interchanged. Binding is the association of the variables or classes to their types. The programming languages can be categorized as strongly typed or weakly typed languages. In strongly typed languages, the violation of type conformance can be detected at compile time. This type of binding variables to their types is called static binding or early binding. In weakly typed languages, the violation of type conformance cannot be detected until runtime. Here, variables are bound to their type only at the execution time. This is called as dynamic or late binding. Static binding is fast but rigid, whereas dynamic binding is slow but flexible. Dynamic binding also promotes expandability of the system. Connected with typing is polymorphism. Polymorphism is the quality that allows one name to be used for more than one different purpose. Polymorphism can be statically or dynamically implemented. For example, different shapes like circle, triangle have the same draw functionality. But this draw functionality is implemented in different ways for each object. Concurrency. This property distinguishes an active object from an inactive one. Concurrency is a property by which a program has several threads of control. These portions can be executed in parallel. To maintain consistency between these parallel threads of execution, locking mechanism is used. Apart from the major and minor elements described above, separation and composition are also important elements to be considered while designing a system. Dynamic modeling. In this video, we are going to see about dynamic modeling. The dynamic model describes the aspects of a system concerned with time and the sequencing of operations. Events that mark changes, sequence of events, states that define that context format, and the organization of events and states. The dynamic model captures control, that aspects of a system that describe the sequence of operations that occur without regard for what the operations do, what they operate on, or how they are implemented. The dynamic model is represented graphically with state diagrams. Each state diagram shows that state and event sequences permitted in a system for one class of object. State diagram also referred to the other models. Actions in the state diagram correspond to functions from the functional model. Events in a state diagram become operations in the object model. The dynamic modeling. Comparison of OO and module-oriented approach. In this video, we are going to see about comparison of OO and module-oriented approach. Module-oriented approach is not the wrong way to analyze and design a system. Object-oriented methodology is not necessarily the right way. A clear comparison of the features of structured and object-oriented approach in analysis and design are given below. SSAD is top-down in nature, while OOAD is bottom-up in nature. The basic building blocks of SSAD are functions in contrast to data in OOAD. SSAD uses functional decomposition, whereas OOAD identifies objects with similar functionalities and groups them together. The basic level of abstraction in OOD is an object, whereas in SSAD it is module. The module summary in SSAD is purely textual and descriptive in nature. OOAD uses class diagrams in the analysis phase itself to show the classes in the system and their relationships. In SSAD, the requirement specification have to be confirmed in all the phases of software development. In OOAD, use cases acts as a link to check up original system requirements. All models formed are verified using use case diagrams. In SSAD, product cost and time increase exponentially with the complexity of the system. So, OOAD approaches are preferred for larger and more complex systems. SSAD has a narrow orientation. It depends on the application and the data structure used. Hence, reuse and maintenance in this approach is less when compared to OOAD methodology. Natural systems follow a top-down approach, so OOAD is referred to SSAD as it follows a bottom-up approach. As objects are the level of abstraction in OOAD, it facilitates easy extension and maintenance when compared to SSAD approach. As OOAD has a higher level of reuse, it reduces the time to market. Further, the system developed has a higher level of productivity when compared to SSAD methodology. OOAD spends more time in design when compared to implementation. In SSAD, less time is spent on design stage. As good design documentation is available in OOAD, errors can be identified and corrected in early stages itself. The following is a comparison of modeling diagrams offered by both these approaches. Use cases in OOAD model requirement are equivalent to requirements document in SSAD. Class diagrams in OOAD perform better when compared to module summary in SSAD. There are no scenarios in SSAD. The ER diagrams in structured models play a similar role to the static models in object-oriented modeling. Data flow diagrams perform similar roles as functional models in the object-oriented modeling. SSAD lacks models corresponding to the dynamic models in OOAD. Hence, it lacks the capability to capture the dynamic aspect of systems. Object orientation is used in evolutionary development. It shows static and dynamic model. Object-oriented approach shows a collection of objects with their method and function. These objects are interconnected to achieve a common objective. Object orientation is a popular method for developing analysis models during the system requirement definition phase, and repairing faults in the system is much easier in approach. It leads to a system that is more flexible to change. Object-oriented methodology requires model at each development phase with technique to convert model developed at one phase to those at the next phase. It is simpler to implement in distributed systems since independent objects communicate through message. One object can invoke method of some other object located in remote computer. It implements object technologies like C++, Java, Cobra, GUI, DCOM. Module-oriented approach. It is most common approach now used to integrate object-oriented design with development process. It is seen as set of function, data, and process and their interrelationship. During this approach, modules are used to create together an analysis which describes the system in terms of object classes. Module-oriented approach repairing faults may require changes in more than one module. As fault identification is difficult, it leads to less flexible systems. In module-oriented approach, each of these modules is used at different development process phase, and there are formal conversion rules from one phase to next. It is difficult to implement in distributed system. It implements new technologies. Modeling using UML. In this video, we are going to see about modeling using UML. UML offers 5 different groups of diagrams to model a system, much like a set of blueprints used for constructing a house. Different diagrams are used for different types of UML modeling. There are 3 important types of UML modelings: structural modeling, behavior modeling, architectural modeling. Structural modeling. Structural modeling captures the static features of a system. They consist of the following: class diagrams, object diagrams, deployment diagrams, component diagram. Structural model represents the framework for the system, and this framework is the place where all the components exist. So the class diagram, component diagram, and deployment diagrams are the part of structural modeling. They all represent the elements and the mechanism to assemble them, but the structural model never describes the dynamic behavior of the system. Class diagram is the most widely used structural diagram. Behavioral modeling. Behavioral model describes the interaction in the system. It represents the interaction among the structural diagrams. They consist of the following: activity diagrams, interaction diagrams, use case diagrams. Architectural modeling. Architectural model represents the overall framework of the system. It contains both structural and behavioral elements of the system. The various UML diagrams and their purpose are as follows: use case diagram, class diagram, object diagram, sequence diagram, collaboration diagram, state diagram, activity diagram, the UML diagrams. In this video, we are going to see about the UML diagrams. The elements are like components which can be associated in different ways to make a complete UML pictures, which is known as diagrams. We prepare UML diagrams to understand a system in better and simple way. A single diagram is not enough to cover all aspects of a system, so UML defines various kinds of diagrams to cover most of the aspects of a system. We can also create our own set of diagrams to meet our requirements. Diagrams are generally made in an incremental and iterative way. There are two broad categories of diagrams, and they are again divided into subcategories: structural diagrams, behavioral diagrams. Structural diagrams. In this video, we are going to see about structural diagrams. The structural diagrams represent the static aspect of the system. These static aspects represents those parts of the diagram which forms the main structure and therefore stable. These static parts are represented by classes, interfaces, objects, components, and nodes. The four structural diagrams are class diagram, object diagram, component diagram, deployment diagram. Class diagram. Class diagrams are the most common diagrams used in UML. Class diagram consists of classes, interfaces, associations, and collaboration. Class diagrams basically represent the object-oriented view of a system which is static in nature. Active class is used in a class diagram to represent the concurrency of the system. Class diagram represents the object orientation of a system, so it is generally used for development purpose. This is the most widely used diagram at the time of system construction. The diagrammatic representation of a class diagram. Purpose of class diagram. The purpose of the class diagram is to model the static view of an application. The class diagrams are the only diagrams which can be directly mapped with object-oriented languages and thus widely used at the time of construction. The UML diagrams like activity diagram, sequence diagram can only give the sequence flow of the application, but class diagram is a bit different. So it is the most popular UML diagram in the coder community. So the purpose of the class diagram can be summarized as analysis and design of the static view of an application, describe responsibilities of a system, base for component and deployment diagrams, forward and reverse engineering, uses of class diagram. Class diagram is a static diagram and it is used to model static view of a system. The static view describes the vocabulary of the system. Class diagram is also considered as a foundation for component and deployment diagrams. Class diagrams are not only used to visualize a static view of the system, but they are also used to construct the executable code for forward and reverse engineering of any system. Generally, UML diagrams are not directly mapped with any object-oriented programming languages, but the class diagram is an exception. Class diagram clearly shows the mapping with object-oriented languages like Java, C++, etc. So, from practical experience, class diagram is generally used for construction purpose. Object diagram. Object diagrams can be described as an instance of class diagram. So these diagrams are more close to real-life scenarios where we implement a system. Object diagrams are a set of objects and their relationships just like class diagrams, and also represent the static view of the system. The usage of object diagrams is similar to class diagrams, but they are used to build prototype of a system from practical perspective. The representation of object diagram. Component diagram. Component diagrams represent a set of components and their relationships. These components consist of classes, interfaces, or collaborations. So, component diagrams represent the implementation view of a system. During design phase, software artifacts, that is classes, interfaces, etc. of a system, are arranged in different groups depending upon their relationship. Now, these groups are known as components. Finally, component diagrams are used to visualize the implementation. Component diagram. Deployment diagram. Deployment diagrams are a set of nodes and their relationships. These nodes are physical entities where the components are deployed. Deployment diagrams are used for visualizing deployment view of a system. This is generally used by the deployment team. Deployment diagram depicts the software components, processors, and devices that make up the system's architecture. The diagrammatic representation of deployment diagram. Behavioral diagrams. In this video, we are going to see about behavioral diagrams. Any system can have two aspects, static and dynamic. So, a model is considered as complete when both the aspects are covered fully. Behavioral diagrams basically capture the dynamic aspects of a system. Dynamic aspect can be further described as the changing or moving parts of a system. UML has the following 5 types of behavioral diagrams: use case diagram, sequence diagram, collaboration diagram, state chart diagram, activity diagram. Use case diagram. Use case diagrams are a set of use cases, actors, and their relationships. They represent the use case view of a system. A use case represents a particular functionality of a system. So, use case diagram is used to describe the relationships among the functionalities and their internal or external controllers. These controllers are known as actors. The use case narrative is used in addition to textually describe the sequence of steps of each iteration. Sequence diagram. A sequence diagram is an interaction diagram. From the name, it is clear that the diagram deals with some sequences, which are the sequence of messages flowing from one object to another. Interaction among the components of a system is very important for implementation and execution perspective. So, sequence diagram is used to visualize the sequence of calls in a system to perform a specific functionality. Collaboration diagram. Collaboration diagram is another form of interaction diagram. It represents the structural organization of the system and the messages sent, received. The structural organization consists of objects and links. The purpose of collaboration diagram is similar to sequence diagram, but the specific purpose of collaboration diagram is to visualize the organization of objects and their interaction. State chart diagram. Any real-time system is expected to be reached by some kind of internal or external events. These events are responsible for state change of a system. State chart diagram is used to represent the event-driven state change of a system. It basically describes the state change of a class, interface, etc. State chart diagram is used to visualize the reaction of a system by internal or external factors. Activity diagram. Activity diagram describes the flow of control in a system, so it consists of activities and links. The flow can be sequential, concurrent, or branched. Activities are nothing but the functions of a system. Numbers of activity diagrams are prepared to capture the entire flow in a system. Activity diagrams are used to visualize the flow of controls in a system. This is prepared to have an idea of how the system will work when executed. Process of object modeling. In this video, we are going to see about process of object modeling. In the analysis phase, a model of the real-world application is developed showing its important properties. It abstracts concepts from the application domain and describes what the intended system must do rather than how it will be done. The model specifies the functional behavior of the system, independent of concerns relating to the environment in which it is to be finally implemented. The analysis model should capture those requirements completely and accurately. In the object-oriented design phase, we define how the application-oriented analysis model will be realized in the implementation environment. Jacobson cites 3 reasons for using object-oriented design. These 3 reasons are: the analysis model is not formal enough to be implemented directly in a programming language. To move seamlessly into the source code requires refining the objects by making decisions on what operations an object, what the inter-object communication should look, what messages are to be passed. The actual must be adapted to the environment in which the system will actually be implemented. To accomplish that, the analysis model has to be transformed into a design model considering different factors such as performance requirements, real-time requirements and concurrency, the target hardware and system software, the DBMS and programming languages to be adopted. The analysis results can be validated using object-oriented design. At this stage, we can verify if the results from the analysis are appropriate for building the system and make necessary changes to the analysis model. To develop the design model, we must identify and investigate the consequences that the implementation environment will have on the design.